Okay, good morning. Let's begin. Today we will pick up from where we left off in lecture 28. So, lecture 29 was the review lecture. So, lecture 29 was the one where we had a review of lectures 12 to 28, and lecture 28 was what we had last covered. So, we pick up from the introduction to OFDM that was given in lecture 28. So, that is our starting point for today. Today's material does include capacity of wireless channels. So, the one of the excellent resources for this is chapter 4 of Andrea Goldsmith's book, Wireless Communication. So, I would definitely encourage you to have a look at that. So, by way of refreshing what we had looked at in the last lecture, we said that Shannon capacity is given by B times logarithm base 2 of 1 plus SNR, and we defined SNR as the signal power by noise power being the noise spectral density times the bandwidth of the signal that we are transmitting. So, given that if you have a channel where the impairment is additive white Gaussian noise, then we know how to calculate the capacity of the channel. So, that was the first result that was established. The second element that was highlighted was that we are dealing with wireless channels. These are not static channels, these are constantly changing because either the user is moving or the environment is changing. So, we have to introduce a variable gain term called alpha. Okay. So, alpha is a function of time, depends on where you are in terms of the location. So, the received signal now has a modified equation. So, the received signal R of t is equal to alpha of t times S of t plus eta of t. Notice that this is the new term, this is, you can think of it as some kind of a variable gain term, okay, think of it as a variable gain. But maybe the correct way to look at it is the effect of fading. Okay. So, gain means it's something signal becomes larger. In the wireless channel, very rarely the signal becomes larger than what you transmitted. So, basically it actually can have a dip in terms of the amplitude. So, actually it's a fading coefficient. So, think of it as a parameter that you have to be careful in terms of monitoring, because it could make your signal level go down. Okay, the next element which we talked about in the context of the wireless channel was whether the signal has got time dispersion. So, let me just draw a figure which will help clarify this point. So, assume that you are transmitting from a base station and you are basically picking up the signal in a mobile. So, assume that there are buildings and objects that will act as reflectors, and for some reason there is no line of sight path. So, let us assume that there is some sort of a obstruction which obstructs the line of sight path. So, the signal basically gets to the mobile non line of sight. So, that is path number 1. Second path is okay. So, basically these two signals, if they have different path lengths, then if this is my transmitted signal, again I am just sort of highlighting it, this is just for illustrative purposes. If I transmitted a pulse, I would receive it from on the blue path with some delay of time, that would come delayed, and the red path probably a little further delayed in time. Okay, so, basically you will see that there is multiple copies that are present, and they actually could cause the signal impairment. Now, let me go back to the figure that we drew last time. If I had only one path, that means I would have only one alpha. So, which means that in time my channel response looks like an impulse. If I look at it in the frequency response, it is flat. So, this is where we get the terminology frequency flat channels. So this would be this would correspond to, this particular one would correspond to a frequency flat channel. Okay, so the frequency characteristics of this channel is that all frequencies experience the same gain. So therefore there is no distortion of the signal. So if the blue line was the signal spectrum, that was what you would receive at the transmitter as well. Now the second case, where there are multiple copies like what we have drawn, and they are coming at different delays. So let us say that for illustrative purposes there are 4 copies of the signal, they are all coming delayed in time. Now yes, this is what the channel impulse response looks like in time. So what is your y axis? This is amplitude, the x axis is delay. Okay, it is also measured in terms of time, milliseconds or microseconds. So this is what it looks like, and the frequency response. Now because there are multiple taps, it is no longer flat, you get some sort of a frequency variation. What you do not want is to have a null, because that means that signal will not propagate at all, but there may be some variations which we do not control. Basically we have no control over what alpha 1, alpha 2, alpha 3 are and what their delays are. So basically if the frequency response of the channel is not constant, then we call it as a frequency selective channel. Frequency selective, okay, and very often we also add the term fading along with it, frequency selective fading. Why did the channel become frequency selective? Because it was dispersive, and then it does not say constant, and it is because of the fading effect. So frequency selective fading channel or a flat fading channel. Okay, so these are the 2 scenarios. If this happens and the blue line is your signal spectrum, you can see that your signal is going to be distorted, and this the receiver will have to undo the effects of this channel. So this is one element that we looked at. Okay, now going back to the context of the capacity. So in an AWGN channel, we define Shannon capacity as the bandwidth times logarithm base 2 1 plus gamma. Now we are in a fading channel, wireless channel, so therefore I cannot talk about a fixed gamma, I talk about a lowercase gamma where it is a variable, okay, and in fact this will be a random variable. Okay, we will come back to that. Right now it is just that it is not a fixed quantity. Okay. So now I would like to highlight what is the impact of the SNR going up and down. So for that we took a particular example. We looked at the at 2 data points. What happens when you look at the SNR at a distance of 100 meters, and then what happens when you look at the SNR at a distance of 1 kilometer, 1000 meters. So basically we looked at 2 examples. We saw that the SNRs are different, and it turns out that in the case of the at 100 meters we get a 153.1 kilobits per second, at 1 kilometer it goes down to 1.4 kilobits per second. So again the impact of SNR is something very important, so we need to keep that in mind. So now translate this to the fading channel. Okay. Basically the fading channel says SNR is not constant, it is going up and down, which means the capacity is going up and down. So we need to now talk about a meaningful reference point for the. So what we then talked about, what we then said is, if you know the probability distribution of the SNR, okay, then what we can say is that we can now talk about a probabilistic capacity. It is B times logarithm base 2 1 plus gamma, but that is only for that particular value of gamma, and that is defined by the PDF, right. This P gamma of gamma is the PDF of the SNR. So we said that, okay, so that is the direction in which we are going. It is no longer a fixed number, it is an ergodic capacity or some number that is statistical. So therefore we are going to explore this a little bit more. So we took a specific example. We said that let us take a channel where there are 3 possible SNRs. by the way, alpha 1 is the amplitude coefficient, SNR means it will be alpha squared. So, we have to take that. So, basically the instantaneous SNR will be alpha squared times gamma. Okay. So, the SNR is alpha 1 0.05 at times with the probability of 0.1, alpha 2 with the probability of 0.5 and alpha 3 being 1 with the probability of 0.4. Okay. So, we then looked at the different values, and I asked you to just quickly verify that you did get an ergodic capacity which came out to be 199.2 kilobits per second. I hope you were able to do that. Let me just add to that with the following additional information. So, basically we are looking at the capacity, ergodic capacity, that is our task in this particular problem. So, we said that there are 3 SNRs. So, there is alpha 1 which will lead to an SNR gamma 1. You should have gotten the gamma 1 to be 0.833. Alpha 2 will be leading to gamma 2 which was 83.33. Alpha 3 leading to a gamma 3 which was 333.33. Now, this corresponded to a Shannon capacity C1 of 26.23 kbps. Okay. Again, you would have done this as intermediate steps. I am just summarizing the final values. 191.94 kbps and C3 being 251.55 kbps, correct. So, notice that all of this is the capacity for just a 30 kilohertz channel. The bandwidth is 30 kilohertz, but Shannon's limit, Shannon's theorem says you can pump several times the bandwidth. So, that means you are doing a modulation that is not binary, but some higher level modulation. So, that is how you will get bandwidth of. So, ergodic capacity which was what we calculated in the last slide, ergodic capacity will be 0.1 times C1, that is the probability of, plus 0.5 times C2 plus 0.4 times C3, which is what comes out to be 199.2 kbps. Okay, please do verify it. And now there is a very interesting parallel observation. What is gamma bar? So, basically there was 3 possible SNRs. The average SNR is given by 0.1 times gamma 1 plus 0.5 times gamma 2 plus 0.4 times gamma 3, that comes out to be 175.1, somewhere in between these 3 values. Now, there is a very important result in coding theory, which or information theory, which you may have studied in digital communications. I will just quote it without result. It is called the Jensen inequality. The Jensen inequality says it basically deals with concave functions. If you have a concave function, if I have a concave function psi of the random variable x, okay, so which means that I will write it as psi of x, that is the, it is a concave function, and if I were to calculate its expected value, this will be less than or equal to, expected the psi of the expected value, psi of the expected value of x. Let me use the correct type of brackets. Psi, blue is for the function, within bracket expected value of x. Okay. So, basically the capacity function, which is basically a logarithmic function, behaves like basically a concave function. So, this ergodic capacity, which is the expected value of the capacity, if I were to now compare it with the capacity of the average SNR. So, basically I would get something which is psi of expected value of x. So, we are looking at the capacity which is given by logarithm base 2 of 1 plus, of course you have to use the bandwidth also, equal to bandwidth times logarithm, this is gamma bar. Okay. So, which means that if it was an AWGN channel with this average SNR, would it be better or worse than my fading channel? Okay. So, if you compute this, it comes out, let me just make sure I got the correct number. Yes, it comes out to be 223.8 kilobits per second. Okay. So, observation, very key observation that comes here. These bad SNRs are killing my capacity. So, that is a key observation, because if I can smooth out, basically take the average SNR, actually I get a much better number. Okay. So, notice that the capacity using average SNR is actually much higher than what I can achieve with the ergodic capacity. So, that is observation number 1. So, we have to be very careful with those channel conditions when the SNR goes low, because that is going to affect our ability to achieve the capacity of the channel. Okay. So, this is an important observation. Now, I want to sort of take this forward and ask you to think about or respond to this question. Now, how will I achieve this capacity? So, basically I have this scenario, right. I have this scenario, sometimes it's gamma 1, sometimes it's gamma 2, sometimes it's gamma 3. So, how do I achieve this, given that I have an SNR gamma 1, how do I achieve capacity C1? It is by saying, I recognize that the channel is not very good, so I apply the appropriate modulation. So, I have to choose the modulation and the channel coding. Remember, Shannon capacity includes channel coding. I will call it FEC, error correction, forward error correction. The combination of these two will help me achieve gamma 1. Okay. So, let me say maybe it is binary modulation with some coding achieves this capacity. Now, I move then from gamma 1 to gamma 2 to achieving capacity C2. Same bandwidth, 30 kilohertz. Now, if I want to achieve higher capacity, I must change the modulation, I must change the channel coding to match the channel conditions, right. So, obviously, and likewise there is a third channel which is gamma 3 to capacity C3. So, this choice of modulation and FEC are very important in us being able to actually achieve the capacity that we are interested in. Okay. So, keep that picture also in your mind. Okay. So, now I want to take this forward. Now, who knows the channel condition? Does the transmitter know what the channel conditions are? In general, no. You just transmit, depends on the channel conditions, the signal will come with an impairment at the receiver. So, the receiver knows the channel conditions. So, always the RX knows the channel conditions, Okay. So, we usually refer to this as channel state information. CSI. Okay, CSI, and by default the scenario that we are looking at is CSIR, that means channel state information known to the receiver, and this is always true because the receiver will receive the signal and it will estimate. But transmitter, it does not have information. Suppose transmitter does not have information. Suppose transmitter does not have the, basically what are we talking about by channel state information? It is gamma I, right. They want to know, you want to know what is the instantaneous SNR there. Supposing Tx does not have CSI information, does not have CSI, what can you do? So basically now the problem being posed is, I want to achieve the best possible scenario, but I should not have outage. So I am going to impose the condition no outage. Okay, what do you mean by outage? I transmit something, but it is received at the receiver with errors. Okay, so if I go back and look at the scenario that we are looking at now, which of these is the most robust transmission schemes? Is it the 1, 2 or 3? Which is the most robust? 1 is the most robust, because you are transmitting with the minimum constellation size with maximum error protection. That's the robust size, because you are likely to make errors, because SNR is bad. Whereas the one that is optimized for capacity, getting the maximum information across, is gamma 3. But if my transmitter does not know this information, then I do not have an option, because you are telling me I cannot say the packet did not get to me, because if I transmit gamma 3 mode when it is actually gamma 1 channel conditions, what will happen? Errors will occur, I will not. So basically no outage means that the only option I have is to stick with the whatever I can get for C1, because that is the most robust mode, and I do not know whether it is gamma 1, gamma 2 or gamma 3. So this is a very important statement, so which basically says that if I insist on no outage when the transmitter does not have information, capacity without outage, if you insist on this, then nothing much I can do. I can only give you C1. This is what you can get out of a channel that potentially could give you 100, 200 kilobits per second. You are going to get only 26.23. Then we sort of get a little bit modified question. We say, okay, I am willing to tolerate some outage. Okay, so capacity with outage, that starts to get a little interesting. Capacity with outage. Okay, we say that, okay, let us say gamma 1 occurs, outage is unavoidable, I am going to sort of take an outage. Outage means that packet will not get through. So then what can you transmit at what rate can you transmit? You must get through at gamma 2 and gamma 3. So which means you can aim for C2, because C2 is designed such that it will go to at gamma 2. Of course, if the channel is gamma 3, which is better, of course the transmission will go through error free. So capacity outage with probability of outage equal to 0.1. That means when gamma 1 occurs, there is going to be errors, but I am going to take that hit. So that means under this condition I can transmit at the rate C2, transmit at C2. So which means that I will get a much higher value, 191.94 kilobits per second, but that is not my throughput. My throughput has to be, throughput is 191.94 kilobits per second into 1 minus probability of outage, right. Only when you are not in outage you can achieve that condition. So this is actually 1 minus 0.1, which is 0.9. So effectively what we have achieved is 172.75 kilobits per second, much better, much better. Okay. So of course if I get a little greedy and say can I go to C2, you will find that the amount of outage is actually more and your actual throughput actually comes down. You can probably an interesting one to just take a look at that and see what actually happens with that. Okay, so this is the overall scenario that yes, if I do not have knowledge of the information channel information at the transmitter, I do have to live with some amount of outage. The time that actually what is getting wasted here is there are times when it is gamma 1 channel conditions which during which time you have transmitted anyway because you did not know about it, and that information got lost. So, you wasted some power.